Three workers at a Japanese nuclear fuel facility set out to complete a routine batch processing task. They were not building a weapon, not running a reactor, and not conducting an unusual experiment. They were preparing uranium solution for fuel fabrication, work that had been done at the site before. Within seconds of a single procedural deviation, an uncontrolled nuclear fission chain reaction ignited in the room around them. Two of the three men would die from radiation exposure. The third suffered serious harm. Hundreds of nearby residents were evacuated. Japan confronted a category of nuclear accident it had assured itself could not happen at a civilian fuel plant. The central question this episode investigates is not simply what went wrong, but why a well-understood physical hazard, one that nuclear science had documented for decades, was allowed to exist inside an ordinary industrial workflow, unguarded. To understand the Tokaimura criticality accident of 1999, you first need to understand what a criticality accident actually is, at a physical level, without operational detail. Fissile material, uranium enriched so that its atoms are more likely to split when struck by a neutron, can sustain a chain reaction if enough of it is assembled in the right geometry, in the right concentration, in the right environment. Below a certain threshold, the material is subcritical. Chain reactions fizzle out. Above it, the reaction becomes self-sustaining. That threshold is called a critical mass. The word mass is slightly misleading because the threshold depends not just on the total amount of material, but on its shape, concentration, and surroundings. Water, for instance, acts as a moderator. It slows neutrons in a way that actually makes a chain reaction easier to sustain in dilute uranium solution than in dry powder alone. This physics has been known since the 1940s. Criticality accidents outside controlled reactors are rare but not unprecedented. The source record shows at least 60 known events globally, in settings ranging from weapons laboratories to reprocessing plants. Several occurred in the 1950s and killed workers. Each one added to a documented body of knowledge about what conditions to avoid. By 1999, international nuclear safety guidelines addressed criticality control explicitly. The hazard was not mysterious. It was catalogued. The JCO Company facility at Tokaimura, roughly 120 kilometers northeast of Tokyo, was licensed to process uranium into fuel. In September 1999, workers there were preparing a uranium solution for a specific fuel product. The task involved dissolving enriched uranium into a nitric acid solution and transferring it through the processing line. Documented investigation findings, including those from Japanese government and nuclear regulatory inquiries, established that the workers used a precipitation tank that was not approved for that step of the process. The approved equipment had been designed with geometry that made criticality physically unlikely. The tank they used instead had a shape that concentrated the solution in a way that the approved vessel was specifically designed to prevent. There is a second layer beneath the equipment choice. Investigations found that the amount of uranium solution added exceeded what the approved procedure specified. When the total accumulation crossed into a critical configuration, the chain reaction began. The workers had no instrument in that room capable of detecting the onset of criticality in real time. There was a blue flash, a visible sign of intense radiation, and the workers immediately understood something catastrophic had happened. Attempts to interrupt the reaction by draining a water jacket surrounding the tank helped reduce but did not immediately stop the chain reaction. It persisted for roughly 20 hours before being brought under control. The three men present in the room absorbed radiation doses that investigations measured or estimated at levels far above survivable thresholds for two of them. Beyond the immediate workers, dozens of JCO employees and emergency responders received measurable radiation exposure. Residents within a several hundred-meter radius were asked to stay indoors. Those within a narrower zone were evacuated. The accident was rated at level 4 on the International Nuclear Event Scale by Japanese authorities, later revised upward to level 4 on some assessments, with acknowledgement that the local consequences were severe, even if broader environmental release was limited compared to reactor accidents. 2 of the 3 workers died, one in December 1999, one in April 2000, from acute radiation syndrome. The third recovered, but sustained documented health consequences. These were the first radiation-caused fatalities from a nuclear accident in Japan. The investigation that followed was extensive, and its findings were unusually direct about the organizational dimension. Regulators and investigators found that JCO had allowed informal work practices to diverge substantially from its approved procedures. The deviation that led directly to the accident was not a spontaneous decision made under pressure that day. Workers had reportedly used the unapproved vessel and unapproved quantities in prior batches of similar work. There was a documented gap between the written procedure and actual practice, and that gap had not been caught by internal oversight or external inspection. This is the organizational cause, and it sits alongside the technical one. The criticality hazard was real and knowable, and the management system that should have kept practice aligned with procedure had failed to do so. The ethical dimension involves more than one party. JCO faced criminal prosecution. 3 workers and a supervisor were convicted under Japanese law. Separately, regulators faced scrutiny over whether inspection regimes had been adequate to detect the drift between written and actual procedures before it produced a fatality. The record shows that the criticality safety training workers received was described in investigation findings as insufficient for the type of work they were performing. Workers were handling fissile material in concentrations relevant to criticality without having received training commensurate with that hazard. That is not a detail about individual error. It is a finding about how the facility conceptualized the risk level of the task. What changed after Tokaimura was a matter of policy, design, and culture, in Japan and in international nuclear fuel processing more broadly. Japanese nuclear regulators imposed stricter requirements on criticality safety programs at fuel fabrication facilities. Requirements around training, procedure adherence, and the physical design of processing equipment to make criticality geometrically impossible, so-called always safe geometry, received renewed emphasis. The accident also reinforced internationally accepted principles that criticality control cannot rely on procedural compliance alone when workers handle fissile material in geometries close to critical thresholds. Equipment design must make the dangerous configuration physically unavailable, not merely prohibited on paper. There is a broader truth the Tokaimura accident demonstrates about complex technical systems and the hazards inside them. The physics of criticality was understood. The safety requirements existed on paper. The people in that room were not reckless by nature. They were operating inside a system that had gradually normalized a deviation until it became routine. That process, the slow drift between documented procedure and actual practice, undetected because no single step looks catastrophic in isolation, appears repeatedly in the history of industrial accidents across industries and continents. Tokaimura is an unusually stark example because the physics involved is so unforgiving. There is no warning period, no gradual onset. The threshold is crossed, and the reaction begins. The decisive force that made the expected outcome fail was not ignorance of the physics. It was the assumption that procedure, training, and worker compliance formed a sufficient barrier between routine industrial work and a phenomenon that kills within seconds of onset. They did not. The accident produced Japan's first nuclear fatalities, prompted a fundamental rethinking of what criticality safety actually requires, and left a documented record that other facilities and regulators have drawn on since. If Tokaimura raises a question for you about how regulatory oversight catches procedural drift before it reaches a threshold event, and why it sometimes does not, That gap between written safety and practice safety runs through some of the most consequential industrial accidents of the past 50 years. This content is for educational purposes only. Do not attempt to recreate any described experiment or procedure.